So, and as before, if people are happier, if people didn't like what we did last time, where we sort of had a side chat, let me know, and we won't do that. But hopefully, it was a way of helping to clarify any things that Carl Henrik was saying. It went right. I think we're ready to go. We're recording. Off you go.
Fantastic. So, welcome back. So today we are going to talk about Gaussian processes. But to begin with, let's do a bit of recap to align the first two lectures and see where we're heading today. So Neil put up this definition of machine learning, right? Which said data plus model plus compute allows us to do predictions, allows us to say something about the world. So the model was where we input our knowledge, and data was the things that we could observe of the system. So now the machine learning scenario is the one where we don't have enough knowledge. So I can't just take my model and take my beliefs about the world, and that leads to prediction. That's not sufficient. It's an ill-posed problem. Neither we have enough data. We need our beliefs as well. So I use this graph here, this Pareto front, to basically explain this. And where I said that the blue line we got here is basically when the problem is well defined, right? And the scenario where I go, I've seen everything I've ever seen before. Now it's a database. It's just a lookup table. If I'm in a scenario I've seen no data, well, now I need to know everything about it. There basically needs to be some form of truth. And machine learning is the thing that lies on this scale, moving upwards and downwards. Different algorithms do different things. So let's take a problem that we can't solve. So it's not on the line. And now we're going to try and make this problem well posed. Let's use as an example that 5 years ago, computers couldn't play Go, right? So now we wanted to somehow move that point, the knowledge that we have about Go and the data that we have currently about Go, to make it a well-posed problem. Well, DeepMind cracked this, right? They cracked this by doing this. They basically took 250,000 years of Go playing, and if you added that, the knowledge that we had about how Go works was actually sufficient to beat the world champion, right? So now, the other way of solving the problem, right, would be to move upwards, to actually try and add knowledge, to try and add understanding about the problem of Go. And now, these two things, even though they're equivalent to solving a specific problem, they become quite different if we add another task, if we add something new to it. Because data is very, very hard to transfer. It's very hard to transfer Go to, say, another problem, say chess or some other game. But the knowledge that you derive is most likely useful because it's something that crosses data. So if we can derive additional knowledge, it's something that we can transfer to additional problems to move us up to this thing. So cool. So that is my way of thinking about how that model plus data compute equals predict that Neil derived, and how we see these two things interplay with each other. So now, the next thing we talked about was saying, okay, so if we're in this state where we take Laplace ID and basically says that there is no such thing as truth, truth is just something that we will never ever reach. We're always going to deal in an uncertain world. The way we said that we can actually formalize this somehow is to think about the scientific principle, where we take some hypothesis. Now, we try to say that this could be mapped onto Bayes' rule. We say my hypothesis is the prior assumptions that I input into a system. Then I have some data, which I now look at. How does my hypothesis explain this data, which is my likelihood? And then by doing computations, I can reach my posterior distribution, which would be how much evidence is there in what I see to update my new hypothesis. That was basically what we think of then as the Bayes rule is an embodiment of the scientific principle, maybe. So the first thing that this means, which is very, very important to see, was this: when we did linear regression and we took this problem of saying, I've got these 2 points and now I'm going to fit some lines to it based on some belief I initially had. We made 2 ones where we had 2 different beliefs, and my updated belief or my knowledge looks completely different. One of them has all slopes being negative and the other one had most of them being positive. So what that means is that if you only get this thing here, if you only get the updated knowledge, you can't interpret that without knowing what knowledge was actually put into the system initially. So what I mean here is that knowledge is a relative concept. To do an example of this, if I give you this quote: "We must speak our minds openly, debate our disagreements honestly, but always pursue solidarity." This was said by a politician due to elections and democracy and so forth. And it sounds really nice, right? This is how I would hope the world would actually work. If I say it was this person who said it, now I think you would quite possibly change your opinion about what that quote actually meant, right? So that's exactly the way we have to think about machine learning models. So then to connect this to what we're going to do today, so maybe last time we talked about machine learning as a framework, and the framework is actually doing this. Now, to me, machine learning as a science is this. So our model is where we input our beliefs about the world. Now, the thing is, there's lots of people who've studied the world for a long time, and humans are incredibly competent. And the type of beliefs that we can actually input in our models in machine learning, the ones that we have mathematically well defined, are not at all up to scratch to what humans know, right? So what the task of machine learning to make it really relevant is to construct what I like to call handles to allow us to input the knowledge that we actually have. That's the key thing that machine learning requires, that we want to do with machine learning, or that we need to develop as a science. So then today, we're going to talk about how can I specify beliefs over larger classes of hypotheses. The lines that we looked at last time wasn't particularly exciting. To do that, we are going to take a completely different way of thinking about beliefs, or not beliefs, but about models. We're going to introduce something called non-parametrics. And this is going to lead to something called Gaussian processes, which is the thing that we're going to talk about mainly. So let's start with non-parametrics. So the problem is this: we're going to go back to our regression problem. I have some data here. I might know something where this data comes from. I might have some set of beliefs. Now I'm going to try and fit these beliefs and see what does this data actually tell me? How can this data update the beliefs I have? Well, we did lines last time. That's fun. We also saw we can do basis functions. That's also fun. We can do polynomials. We can come up with all sorts of different parametric forms, and then we can apply the learning principles that we derived. But having done so, we've made a hard choice on the specific type of functions that we've chosen. And that's very, very strict, right? And also, how is it possible to even define all possible types of functions? Well, that's tricky. So we're going to think about this in a different way. So I'm going to use the example of beer to explain this. So now I like beer. Beer is very nice. Now it turns out that Neil also likes beer. So now I had a very nice beer yesterday. So now I want to explain this to Neil and say, you know what, you should really go and try out this beer because I think you'll like it. So one way, the parametric way of explaining this to Neil, is that beers are very well parameterized by recipes. So now I can say, this is the recipe for this beer, and now Neil can make up his mind if he should go and try this. Now, even though we don't like beer, both of us, we're not good enough to take the parameterization and get that to the taste of what beer actually is. We're simply not good enough at this. So another way to do it is that thankfully, I've had quite a few beers together with Neil. So what I can do is that I can say, you know what? I had this lovely bitter yesterday. It tasted a little bit like that Yorkshire bitter that we had. The head was quite similar to that. But then the body had this hoppiness from that New Zealand IPA we had in the free press the other week. Wow, that's an explanation that I think works much better for us. So now what I've done is that I explained the beer by relating it to previous experiences without parameterizing it. And that is non-parametrics. So let's take this as a more concrete example. So here's the beer that I want to explain, or I want to explain this point. Now, if we've had other beers, so for example, this red point, now what I can parameterize how similar the black one is to the red one. That's the way I communicate my knowledge. So the first benefit of this is that the more beer I drink, effectively, my representational power gets stronger. Now, you can also think that effectively, how many red points can I get? Well, I can get as many as I want. The more data I see, the stronger my modeling capability becomes. So now, the key thing here now then is how do I relate these points to each other? Well, the simplest thing is to just say, well, actually, I have some measure of similarity, and I'm always just going to report the most similar one. That's the thing I can transfer. This is then what we call a nearest neighbor algorithm, which is the simplest form of non-parametric algorithm you can think of. The other way is that I could say, I could define some form of distance measure. So here, the squared Euclidean distance, where I now say, well, I use this to relate it. This is the strength of how similar these things are. Or I can take something like a shortest path algorithm, and I can say, actually, this is how they're similar to each other. So now that is effectively non-parametric. So what you do is you do not think about the parameterization of the red point. You think, or the black point, you think about how the black point relates to the red points. So now let's take this analogy. I might drop the beer analogy for now, but let's take the non-parametricness and take that to the level of functions instead. So now we have functions. Functions live in this space here we got in front of us. So now we need to somehow have a handle on what we are going to relate to, do non-parametrics over on the space of functions. So what is it that we actually can observe of a function? Well, we can observe the output. So if I take the line at x equal to 3, this line goes from -infinity to positive infinity. Now I know that any function that is defined at this line can only cut this line once and only once. So now we want to be a bit probabilistic. So what we're going to say is that we're going to say that I'm going to define my belief over where I think the function cuts the red line. Now we're going to say that that's Gaussian. So the nice thing about this, the very nice thing about using a Gaussian to parameterize this distribution is that first, the Gaussian does never go down to 0, right? That means there's a non-zero probability for every possible intersection. The other thing is, I can parameterize my Gaussian to be very, very tight and super narrow. That means I can have a very, very strong belief in where I think the function intersects that line. I can also make it very, very wide, which means I can specify if I have a large ignorance over this. So now I made that argument at 3. I can also make the same argument at -2. So now I got these two Gaussians, and I say that each of them parameterizes where I think the function cuts this. So now comes the first step. We are not going to consider these two as independent Gaussians. We're going to consider them as joint Gaussians. And why is that? Well, any interesting function, knowing the location of one should say something about the location of the other, right? If they were independent, that means these two slices don't share any information about each other at all, right? So what we're going to do is that we're going to say that these two function values, the intersection of the function at the green and the blue are called f, and they follow a joint Gaussian distribution that has mean mu and this 2 by 2 covariance matrix. So now let's say that you actually gave me the value at the green line. You said that at -2, the value of the intersection is 2. So now we haven't known each other for very long, so I don't trust you completely. So I'm going to say that the value that you gave me, I'm now going to say, well, actually, I still don't believe you completely. So there's a little bit of wobbling around here, and that's clearly still a Gaussian. Now, the non-parametric question now is, what does that knowledge, what does having drank that beer tell me about other beers effectively? So specifically about the red one. So you can think of an example where it says, well, actually, knowing the green one doesn't update my information at all about the red one. So the red one is exactly the same as it said when I only looked at the red one. Or knowing the green one tells me everything about the red one, and now I just transfer this Gaussian. Or most likely, it's somewhere in between those things, right? So now, if we then look at Gaussians, and if you derive the Gaussian identities in the worksheet, you will know these, you've already derived these equations. So if I take a joint Gaussian here, and I say that the covariance element is 0.5, so now these are the two slices. Now, if I now look at the output, which is the function value, this is the green slice and this is the blue slice. If I now say I know you gave me the green slice at 0.5, the conditional distribution then gives me the distribution of what I think the slice or the intersection should be at x2. This is just a conditional distribution, right? Now, of course, if I change and make the covariance element higher, I get the joint distribution, which is much more peaked. And now the information between the two are much, much stronger. If I know it's -1, then I get a distribution which is very peaked around -1 for the other. If I instead make it independent, so I make it 0, of course, now no information is transferred. All the conditional distributions are exactly the same. So effectively, the covariance element is the thing that allows me to define how much information is transferred between these two slices. So a large covariance means a lot, a low covariance means a little. So let's just do this. Let's now draw some samples from this. So we take our two slices, our green and our blue. I take this two-dimensional Gaussian and I draw a sample. So I draw this sample, which is slightly -1.5-ish along the green one. So here, and then it's close to 0 along the red one, and I get this. Now, what I can do is that I can, of course, draw a couple of others, and I get these values. Now, we can change the Gaussian, and if I change the Gaussian and make it very, very correlated, now, of course, you can see that if I pick a value here, I get pretty much exactly the same value on the other side. If I make them independent, they go all over the shop. So, now the question is, that was two slices. How many of these slices can I draw? Well, I can clearly do 3, and I can do the same process and define a 3-dimensional Gaussian. I can do 4, quite possibly I can do a lot of them, right? So I can do tons and tons of slices. So let's say I do n slices. And now I can define this n-dimensional Gaussian instead, where I got the output here, all the f's, the n's I picked, I got the means, and I got this covariance object, which is now n by n. So now comes the really, really cool thing about the Gaussian distribution. And this here is, we need to see how the marginal distribution looks like. Again, this was in the worksheet, so you might have proven this as well. So if I now take a Gaussian, a two-dimensional Gaussian in this case, that is specified that just has mean mu1, mu2, and this covariance. If I now pick out the marginal distribution over x1 by integrating out the others, I get this. Now, if I instead take a much, much bigger Gaussian, so I take this huge Gaussian, but I keep the mean and the variance element for 1 exactly the same. If I now integrate out all the n elements of this, I reach exactly the same distribution. So this is what's called the marginal property of the Gaussian, or if you take Carl's course in engineering, he's going to refer to this as consistency. So what this means graphically is this. If I take this joint Gaussian distribution here, now this is the marginal distribution over x1. If I now change the covariance object and the variance object for x2, I get this joint distribution. But the marginal distribution over 1 stays exactly the same. So now, this allows us to do something very, very cool. So what this means is that the marginal is consistent. So if I now take 2 slices, just as before, and I draw this thing, that's exactly what we did. Now, I can say, actually, I want to take a 3rd slice, and I'm going to take that in the middle. So now I do that. Now what you see is that now I fix the random seed for 1 sample, just to remember. These 2 stays the same. I've just taken an additional slice. Now that's 3. I can do 5. I can do 9. I can do 17. Now this here is picking out 17 slices, drawing a sample from a 17-dimensional Gaussian, and then plotting lines between them. And now that looks like an awfully nice curve. Now, just to show this again, I can take 10 of these. The random seed is consistent along 1 sample. 2-dimensional Gaussian, 3-dimensional Gaussian, 5-dimensional Gaussian, 9, 17. Now that here looks like, if you've seen them before, samples from a Gaussian process. It's still not the Gaussian process because this is just a Gaussian distribution. So now the question is, how many of these slices can I draw? How many slices can I draw along the real line? Well, I can draw infinitely many, right? I can enumerate infinitely many slices using the real line. And that is what the Gaussian process is. So a Gaussian process is effectively an infinite dimensional Gaussian distribution. And that's it. Now, the way I like to think about it is this. So I have the infinite world, which is on my left, where a GP is defined. It's an infinitely big Gaussian distribution. Then I have a projection matrix. And this matrix picks out n sets of marginals and creates a Gaussian distribution. This Gaussian distribution, I can then do this cool thing to draw these function-looking things. The important thing with this is that independently of which projection matrix I pick, which marginal I pick, this Gaussian distribution is consistent with this process. And that is the cool thing. That is what's called the marginal property. So if you want to think of the definition of this, the way we think about definition or GPs in the definition when we work with these as prior sort of functions is like this. A Gaussian process is a collection of random variables. The random variable here is the output of the functions who are jointly Gaussian distributed. That's that each of the function values follows a joint Gaussian distribution. And this collection is indexed by an infinite index set. The index set that we've used so far is the real line. Cool. So now comes then the question that's great, right? That's really nice that this works, but how do I actually parameterize this infinite dimensional Gaussian? Well, the way we parameterize it is this. We parameterize the mean as a function of the input, and we parameterize the covariance as the function of two input locations. So we have two functions, and these are parametric functions, mu and k. If I can parameterize them, and these two functions are defined over the whole index set, then I can compute as big of a Gaussian distribution as you ask me to. So that is a Gaussian process. So this object here, the covariance function, is the thing that's really interesting. So the mean effectively only shifts each slice up and down. But the covariance is the thing that parameterizes how much two slices share information. Effectively, how much one beer tells me about another beer. So the index set to this is the uncountable infinity, because effectively any subset I take of the real line, I can take infinitely many slices. Then if this now is effectively your handle to input knowledge into the system. If you have a problem where your knowledge is related to, in one way or the other, where you can say something, well, actually, if I know this, that tells me this much about this, then a Gaussian process is a very, very good parameterization to input your knowledge into the system. So one thing that you can do, which is the thing that we've done so far, is that we parameterize smoothness. So we've effectively said the further away you get from a slice, the less things covary. So we can parameterize this, for example, using an exponential fall off with distance. So now here, if we draw samples, I think I took 300 dimensional Gaussian here. So I picked 300 slices, drew lines between all of them. Then I get this thing. I can make the fall off quicker. Now I'm going to get wigglier lines, or I can make the fall off much slower, and then I get less wiggly lines. So that's one way you can do. You can think about lots of other ways of parameterizing this knowledge. So, for example, you might know that your knowledge is periodic. So now what you can have is that you can have that the covariance decreases and then it increases back up again. If you would parameterize a function that has this behavior, you will get periodic samples. Cool. So that is specifying the GP prior. So now, hopefully, we've been given this tool that we can possibly use to input our knowledge into the system. But there's an additional cool thing that we haven't talked about. And that is now we want to mix our model with data. So now we want to do inference over this. So if we want to do this, this is the problem that we have. So now the way I'm going to use this, the notation is that I have some data that I've seen, F, and then I want to say something about another set of slices, F star. So now, if we do base rule on this, I need to take the joint distribution, and then I need to normalize that with the distribution over only the things that I've seen. So that implies I need to compute this integral in the denominator here. So now let's think about what that integral actually is. So that integral, if we do the product rule, we can split it up like this. So effectively what this means, if we take the analogy that we took with sums last time, so that means I draw every possible function that I have, that I can, at location x star, according to their probability. We've already said that this distribution doesn't exclude any intersection points, so there's going to be quite a lot of them. And then I plug it into this element, and then I check if that function at these points are consistent at the other points. So now that's an awful lot of functions. So effectively, let's think about it like this. So this here is my samples from F star, P of F star. Cool, that's how they look. And now I want to create an if statement that checks which ones of these go through that point, and then I exclude all the ones that don't. That's going to be a very, very big if statement. It's going to be a for loop over infinitely many functions. So this you don't want to do. Now comes the beauty of this, because we don't have to compute that integral. We can be a bit clever. So let's go back to the definition. So this object here is the joint distribution of the data that I've seen and the data that I want to evaluate my updated knowledge on. So now the joint we've defined. We define this as a Gaussian process. Now this term, the green one, which is the distribution over the data that I've seen, well, we know this through the marginal property of the Gaussian. And we know that these things, this is consistent with this. So the only thing I need to do is that I know that this is also Gaussian. So the only thing I need to do is to solve for this. And now that is just a conditional Gaussian. And you did this in the worksheet for a two-dimensional case. So effectively, what we do is that we've specified this big Gaussian distribution. Now you just solve for the conditional, and that's going to look exactly like this. So now let's just think of what we actually did. So we have this Gaussian distribution or Gaussian process. We got this infinite thing. Now I say that I've seen 7 points on this. So the x-axis here is effectively 7-dimensional, to take this analogy. Now I want to evaluate 300 other slices. So the y-axis is 300-dimensional. So what I first do is I pick down this 307-dimensional Gaussian from the Gaussian process. And then I condition 300 dimensions on 7 dimensions. And then that gives me this 300-dimensional conditional, which I can now draw samples from. And that's it. So let me show you how this makes sense and what this actually does. So here's 7 points, the 7 points that I talked about before. Now I want to know for 300 other points, F star on these. So what I'm going to do is that I'm going to compute the conditional Gaussian, or the predicted posterior, as we call it. So the first term, the mean of that Gaussian, looks like this. So it's effectively a matrix multiplied by the values I've already seen. If we look at what this matrix looks like, it looks like this. So you can see it's 300 times 7. So effectively, the first row of this is what you multiply, the 7 coefficients that you multiply with the points that you've seen to get the new point. So you can see that in the beginning, now we're somewhere out here, far away from the data, we're basically multiplying 0 by the values that we have. So effectively, out here, it says, well, actually, the data provides me with very, very little knowledge, so that I'm going to go back to the prior mean, and the prior mean is 0. Then as you go closer, here somewhere around 0.60, 70, now you're somewhere close to here. What that means is that you're going to start putting a non-zero value that multiplies with the first point here. Then somewhere close to 110, you're probably somewhere in between these 2 points. And now you're going to take a weighting between these two, because you got the non-zero value on both these. So effectively, it's just a linear combination of the data. So then let's look at the covariance elements. So the covariance of that predictive Gaussian looks like this. The first matrix is this. So that's just my prior, my Gaussian process prior. It says the points close to each other covary, and then the further away they get, they don't covary very much. This second term looks like this. And then when I subtract this from this, I get the posterior of the predictive distribution, which basically just says, far away from where I've seen data, you go back to the prior. When you get very close to the data, you don't have any covariance at all. These values are all very, very small. So that's effectively what means if I sample from that distribution, I get something that looks like this. I get far away from the data, I get things that looks a lot like the prior. When I get close to the data, I get I go through the data point and have no variance left, and then the variance goes up and so forth. It's just a linear combination of the data to predict in between. Another way of showing this is, rather than showing samples, is to show the mean and the variance, which I've shown here. And this can be instructive, but it can also be a very dangerous plot to do. I will highlight this in the next lecture. To hint at something that we're going to do, now I'm going to show how basically, if I see data one by one, how does my belief get updated? This is exactly the same plot as we did with the linear regression when we saw the prior and then changing into a posterior that was narrower and narrower. So at first, I have this prior. All slices are the same. I have this function, which I'm now going to observe 1 point after the other. So I observe 1 point, 2, 3, and you can see with the prior assumption of smoothness that you says, if I know something, the contribution of that point is that it co-varies strongly with things that are close to it, then I get exactly this behavior. So that is how a Gaussian process prior works when we look at data. But we didn't actually look at data. So really what we've only done so far is look at the prior, and we've really looked at what I would potentially call the conditional prior, not the predictive posterior. So what we haven't done is that we haven't introduced the likelihood function. We've just taken conditions on the prior, and you can do that because it's non-parametrics. So if we would do exactly the same argument with explaining away as we did in the linear regression case, that says that I have my data and then there's some Gaussian noise around it, we can derive a Gaussian likelihood. Then we can say that given that I know the location of my function, so the output from the model, then I can say that the value of the data that I observe is just independent. I can now just derive this very simple likelihood function that looks like this. So what we want to do is that now we say that if I see data y, now I explain away some variance in this before I explain it with my function. So this actually becomes super easy to do. So now instead of specifying a joint distribution over f and f star, now I got y and f star, and I just add an additional variance to y, which doesn't depend on x, which is just this independent noise that I add. So the predicted posterior becomes exactly the same, except for that you just add this additional term that doesn't depend on x. And if I then draw samples from this using the same procedure, now you can see that all samples don't pass through the data points that I've seen. I can increase the noise and get them to go even further away. Or if you look at the process of this, you can see that here I got 1 degree of explaining away. Now I can increase the noise, and eventually I can explain away everything using the noise, and then just fit a straight line, which is coming back to the prior that I started off with before. The noise effectively explains away all the variations that I have in the data. So I think I'm going to wait with that one for next time because we're running a little bit out of time. So that's basically Gaussian processes. So basically, the things that we talked about was non-parametrics and a non-parametric formulation of functions. The idea with non-parametric is that instead of parametrizing the relationship or parametrizing the function itself, you parameterize relationships between data. And you effectively can think about how much information does knowing this tell me about everything else. If you can parameterize this, a non-parametric model is super useful to do. So in a Gaussian process, in terms of implementation, and I really think this is one thing that people usually find very hard. So the tricky thing with understanding GPs is understanding how ridiculously simple they are. The plots I showed with these wiggly samples, that's about 4 lines of Python code. Pretty much 4 lines of Python code. You're going to do that in the worksheet. So when you implement it, it's just a big Gaussian distribution, a very big one, but that's it. In theory, and this is what this marginal property and all these nice things comes from, the theory is that you can think about this Gaussian as coming from a projection of this infinite object, which we call a stochastic process. So now there's one thing I just wanted to highlight a little bit. So a question that I usually get is people say, well, cool, this is a nice way of thinking about distributions as the distribution comes from this infinite dimensional object. Does all finite distributions that we have a generalization in terms of a stochastic process? And it turns out quite a few have. So there is something called Kolmogorov's extension theorem. And what Kolmogorov's extension theorem defines is the 2 conditions that we need for a finite dimensional measure to be a generalization or a realization projection of an underlying stochastic process. And these 2 are the exchangeable condition and the marginal condition. We just talked about the marginal condition, but the exchangeable one is trivial for a Gaussian as well. And if you want, you can look at these. And if you're taking L49 in engineering, you're going to see another object like this, which is called a Dirichlet process, which is effectively the extension of the Dirichlet distribution to an infinite dimensional object. But I am going to end there with this. there is a worksheet uploaded, which I really recommend you to have a look at. And I also think a good thing to look at is actually coming back to the Gaussian identities and looking at the linear regression equations, because you're going to see, this was the thing that I skipped, you're going to see that they're exactly the same. We're effectively doing very little difference here to what we did in linear regression if you look at the predicted posterior. I'm going to talk more about that next time and relate it to a little bit more. But that was about what I had. I'm going to stop sharing and see. Very good.
Should we stop recording and then we can ask questions and people won't have to worry that they're going to be recorded in their questions?
Yeah.
In case people want to stick around.